All right, well, welcome to our recording for section 7.3. So, starting a new topic, building on the idea that we've been developing that there can be alternative ways to build equations for curves, but we're going to do something in this section that is even a little more different than what we were doing previously. So, let's have a look at our outline for section 7.3. So, in previous sections, we examined an alternative approach to creating equations for curves that was parametric equations. Okay, parametric equations were different from the standard equations we'd been using, and we saw that they had some pros and cons to them. Okay, the biggest con to parametric equations is just that we're not as used to using them, so sometimes it's easier for us to understand what's going on if we convert back to a standard equation. But parametric equations still use the same coordinate system as standard equations, x and y, horizontal position, vertical position. In this section, we'll introduce an alternative way of tracking the position of a point in the plane, polar coordinates. Okay, now we're not doing this just for fun, although I will kind of enjoy it. We're doing it because sometimes it's easier to use polar coordinates to create an equation for a curve. In particular, the type of curves that we don't always represent as functions, because if we think of them as functions, then they wouldn't pass the vertical line test and we'd have to break them up, and we'd rather treat them as a whole. Okay, things like the conic sections that we've already started talking about a little bit, ellipses and hyperbolas. Okay. In particular, as we move into multivariable calculus, a lot of you will do that taking Calc 3, you're going to find that we deal with those sorts of curves quite a bit more than we have been. We've largely avoided them up until now. Okay, for most of our treatment of calculus, we've brought them out occasionally. Okay, but with polar equations, those types of curves are often easier to work with. And in particular, if your goal is to integrate, it is frequently easier to integrate areas bounded by circles and ellipses and other types of curves with some type of radial symmetry to them. Okay, if we put them into polar coordinates, so this will, like most things we do, expand the amount of things we can do. All right, so let's see what this is about. We're going to start with a rectangular point. Okay, so something written just as an x value and a y value. Okay, the point 4 comma 4 square root of 3. Now I know it's a little bit screwy to have that square root of 3 in there. Okay, 4 times the square root of 3 is like 6.9. Okay, I just punched it up on my calculator. I chose that because it'll be nice for what we're going to do with it. But first things first, let's have a little look at Desmos, and let's just type in parenthesis 4 comma 4 sqrt 3 and close that. Okay, well, remember I said that that my y value here, 4 square root of 3, is almost 7, so it looks like that would actually be off the screen, so maybe we need to zoom out a little. There we go. Now I can see it. Over 4, up almost 7. There's my point. Okay. Now, let's make a couple computations for this point. Okay, starting with, let's compute how far it is away from the origin. Alright, so here's our point drawn on a piece of paper here. Okay. If I want to compute its distance from the origin, I can use the Pythagorean theorem. Okay, if I can imagine drawing in a right triangle where the horizontal and vertical sides of that right triangle are the values of my x and y coordinates, then to get this side, which we're going to call r, okay, you might remember using r for this in trigonometry. In that context, we meant r for radius, and it's basically playing on the word radius here. If I call that side r, I can use the Pythagorean theorem to find r. So in particular, I can say by the Pythagorean theorem, r squared equals the x coordinate squared plus the y coordinate squared. Okay, so r squared equals, looks like that would be 16 plus 16 times 3. The 4 gets squared and the square root of 3 gets squared. And, well, let me see. 16 times 3 is 48, plus 16 is 64. So r squared is 64, and that implies that r is 8. Okay, so that's our distance from the origin for this point. It's 8. Okay, this was part B on the outline. Let's have a look at what part C said. Okay, so we plotted it. That was part A. Part B, we found our distance from the origin. And now, compute the angle between the positive x-axis and the line connecting the origin to the point in radians. And we'll call this value theta, something we're accustomed to using for angles, especially angles in radians. Okay, well, let's have a look at that. So if theta is the angle between the line that connects the point to the origin and the positive x-axis, then this would be theta right here. Now I have several options here, but I would like to make use of the two sides that I knew from the get-go. I mean, I now know that r is 8, but I'd like to be able to get theta without having to compute r first. Okay, I want to try to keep these independent. So it looks like I'm going to use the side opposite and the side adjacent, which is just the y value of the point and the x value of the point. Okay, and using just my basic trig definitions, opposite over adjacent is tangent. So I can say that tangent of theta is 4 square root 3 over 4, which implies that tangent of theta, if I simplify, is square root of 3. Okay, now if you remember your angles, you will remember that the angle in the first quadrant whose tangent is the square root of 3 is pi over 3. Okay, if you don't remember your angles, you can always put your calculator into radian mode. So let me just double check there. Yep, RAD. I know it's kind of hard for you to read, but it's in radian mode. And then say, alright, I want to reverse a tangent. I know what the tangent value is, but I want to reverse a tangent. So I want to do a tangent inverse of square root 3. Close the square root, close the tan inverse. Now, that decimal may not immediately be recognizable to you as being pi over 3. Okay, but if I take pi and divide by that, pi divided by answer, okay, that tells me it was pi over 3. What else could I have done with that number? Let me see. What would I get if I divided that by pi? So that'd be 1/3. I'm trying to think of a kind of a clear way to do this. So we came up with theta equals 1.047 ... And the question is that some number times pi? Okay, well if we divide by pi, it'll tell us what that number is. So I'm going to say that's probably the thing to do. Okay, divide by pi. Okay, and I got 1/3 when I did that. I accidentally did it twice. Alright, there's my number, there's my decimal, but what multiple of pi is that? Well, let's divide by pi. I get 1/3. Alright, so that number was 1/3 pi, or pi over 3. So that's what you could do if you don't just remember that the angle whose tangent is square root of 3 is pi over 3. I know at one time you probably had your unit circle memorized, and maybe you don't still, and that's okay. You can rely on technology. It'll start to come back because you're going to start seeing this stuff a lot. Alright, so what we've done is we've computed the distance from the origin and the angle. Now those two things actually are enough to pin down the point. Okay, if I tell you how far it is from the origin, and I tell you how far that distance is rotated off the positive x-axis, that actually pins down the point. So if I gave you those two values, my r value and my theta value, which were 8 and pi over 3, that would actually be just as good as a way of giving you coordinates for this point. So rather than telling you how far to go over and how far to go up, I'm telling you how far to go out and then how far to rotate. So you could almost think of that as like, alright, it was 8 comma 3, so come out a distance of 8 and then rotate pi over 3, and that would get me to the same point. These are what we call polar coordinates. Okay, the r value is what we would call the radial coordinate, and the theta is what we would call the angular coordinate. Alright, let's see where that puts us on our outline. Well, let me see, we just did part D. Graph this point on polar paper. Alright. So let's have a look at some polar graph paper here. Now, I want you to know that I got this by just doing a web search for polar graph paper. That's all I did. Okay, and I immediately found some printable polar graph paper. Okay, you could do the same thing if you want to get some and print it out. Okay, so if I want to graph this with polar graph paper, notice how this paper is set up. Okay, these lines coming out from the origin are measuring angles. Okay, if I go from 0 to 90 degrees, that's really 0 to pi over 2. I've got these three darker lines that divide 90 degrees into, I guess that'd be 30 degrees, 60 degrees, 90 degrees, or pi over 6, pi over 3, pi over 2. So these lines coming out of the origin measure angles, and then these circles measure distances, as each circle has all the points that are a certain distance from the origin. This circle has points that are 1 unit from the origin. This circle has points that are 2 units away, and then 3 units away, and so on. So if I want to plot the point 8 comma pi over 3, what I can do is I can start at the origin, and I can count out 8 circles. 1, 2, 3, 4, 5, 6, 7, 8, and then I can follow that circle until I get to the radial line for an angle of pi over 3, and that gives me the point that's 8 units from the origin, and pi over 3 radians rotated from the positive x-axis. Okay, so I would actually recommend, as you do the homework, find some polar graph paper online and print some out. I think you'll find that it helps you get the idea to have something that's set up just for this purpose. Now let's flip back over to Desmos. Okay, Desmos, it is actually possible to, if you click on this little wrench over on the right hand side, you can tell it to change the grid from a rectangular grid to a polar grid. Okay, and if I do that, I can see that, well, let me see. Here's the circle that's 8 units out from the origin, and then if I follow that circle, I can see I'm on the line that corresponds to an angle of pi over 3. So there's our point, 8 comma pi over 3. Okay, we graphed it in rectangular coordinates. Okay, it's in the correct place, but now I can see the polar coordinates by switching my grid over. Alright, Well, let's go back to our outline once again. Alright, that completes part F. So, key ideas for this section. Well, I mean, this is the big thing right here, the definition of polar coordinates. Okay, we just found some radial and angular coordinates, an r value and a theta value. Okay, the book introduces those on page 642, the first page of section 7.3. Have to scroll down here to the bottom. Okay, it tells us that first coordinate is the radial coordinate, the r, looking at this, and the second one is the angular coordinate. And it went through how to compute them, okay, using trig functions as we did. Okay, so those are our first major definition. You know, what it means to be polar coordinates. You have to have a radial coordinate that measures distance from the origin, and an angular coordinate that measures angle off the positive x-axis in radians. Alright, back to the outline. Okay, what I'd like to do now is I'd like to just practice kind of using these coordinates using some polar graph paper. So I've got some points here I want to plot. Let's plot these points. So what have I got here? I've got 3 comma pi. Okay, 3 comma pi. Well, let's go ahead and graph that. Okay, so for 3, I want to come out to my third circle. So, by the way, I'm not counting this here as a circle. Okay, these little light, there's 2 light circles and a dark, and they come in sets of 3. Light, light, dark, light, light, dark. So this isn't really meant to be a circle. This is just kind of highlighting where the origin is. Alright, so I'm going to come out 1, 2, 3 circles. Now I'm a distance of 3 away from the origin. And now I've got to go through an angle of pi radians, which of course is 180 degrees. So I'm going to trace my circle that has a radius of 3, just to keep my position, until I've gone pi radians, and there's my point. So we'll call that point 3 comma pi. Alright, well, what was the next point on my outline there? The next one was 2 comma 5 pi over 3. Okay, now remember, for these, this is pi over 6, this first darker line. Okay, this one's pi over 3. It takes 2 dark lines to make 1 pi over 3. So there's 1 pi over 3, 2 pi over 3, 3 pi over 3, which is just pi, 4 pi over 3, and 5 pi over 3. Okay, now remember, the point was 2 comma 5 pi over 3. So let's come into the circle that has a distance of 2 from the origin, but stay on this radial line for 5 pi over 3. So 2 comma 5 pi over 3. So the thing that I want to be clear is that this really works just as well as x and y. Okay, either way, I need 2 bits of information to nail down a point in a plane. I either need a distance over and up, okay, and over could mean right or left, and up could actually also mean down. Okay, but I need a horizontal distance and a vertical distance, or I need a raw distance and an angle. Either way, I can knock down the position of a point with 2 coordinates, either 2 rectangular coordinates or 2 polar coordinates. Alright, what was the next point? Next point was 7 halves, comma 3 pi over 4. Okay, well, pi over 4 would be halfway to pi over 2. So pi over 4 actually isn't very marked very well on this. Pi over 4 is halfway between 0 and pi over 2, so it's halfway between pi over 6 and pi over 3. So pi over 4 is actually kind of in between these 2 lines here. Okay, but think of it in terms of 45 degrees. 3 pi over 4 would be 3 45-degree angles. So 1, 2, 3. Alright, 3 pi over 4 takes us halfway through the second quadrant. And what was the r coordinate was 7/2. Okay. Well, if the r coordinate was 7/2, that's 3.5. So let me think here. I want to come out 1 circle, 2 circle, 3 circles, not quite 4 circles. I want to be in between the 3rd circle and the 4th circle. And I also want to be in between these 2 radial lines. Now, some types of polar graph paper will have a line right on those 45-degree increments. Okay, that's actually kind of better. Okay, I got this one because it had lots of lines, but unfortunately it doesn't have a line right on 45 degrees. No biggie. So 7/2, comma 3 pi over 4. That's our point there. Alright, let's continue practicing. The next one is 6 comma negative pi over 6. Alright, so I have to count out 6 circles from the origin. 1, 2, 3, 4, 5, 6 circles. Now it's negative on the angle, so that means I go clockwise. So this would be the point 6 comma negative pi over 6. Okay. What else do we have? Oh, we've got a point with a negative r value. So negative 2 comma 2 pi over 3. Negative 2 comma 2 pi over 3. You know what? I think my graph's getting a little cluttered. So I'm going to go ahead and go to a clean graph. Well, let me see. Let's find 2 pi over 3. That's pi over 6. That's 1 pi over 3. So I need 2 of these wedges to make a pi over 3. Alright, so here's 2 pi over 3. Okay, so now that I've got the right radial line, I need to come out 2 circles. Oh, but remember it said negative? Here's the thing about negative r values. If the r value is negative, that actually tells you that you should go the opposite direction. So rather than coming up into quadrant 2, I'm going to follow the radial line that's exactly 180 degrees off of the one for pi over 2. Okay, because my r value is negative. So that's going to put me 1 circle, 2 circles. It's going to put me right there. Okay, so that's the point negative 2 comma 2 pi over 3. Now we actually graphed this same point up here. We graphed it before as 2 comma 5 pi over 3. 5 pi over 3 is, well, it's pi more than 2 pi over 3, or 180 degrees more. So by using a positive r value and a bigger angle, we were able to get to the same point. That's something about polar coordinates that's actually a little different than rectangular coordinates. With rectangular coordinates, each point in the plane has only one way to represent it with x and y values. But when you're using polar coordinates, there's multiple ways to represent it. In fact, there's really more than 2. Okay? Because I could have just used an even bigger angle. Remember, if you add 2 pi to an angle, it just takes you all the way around the circle. So 2 pi is 6 pi over 3. So if I had made this, instead of 5 pi over 3, let's say I made it 11 pi over 3. Okay, if I had made it 11 pi over 3, then my angle would have been all the way around to here, and then all the way around again, and I still would have ended in the same point. So actually with polar coordinates, there's really an unlimited number of different ways to represent each point, because we could just keep adding multiples of 2 pi and getting different angle representations. But there's usually only 2 choices for r, a positive choice and a negative choice. And that would change what you picked for angles. So that's just something that's a little different. The big thing you need to know is what to do when r is negative. When r is negative, you're actually going backwards. Alright, which I think makes sense. Well, let's see what else is on our outline. Alright, here's a point that's in polar coordinates, 8 comma pi over 6. Let's convert that point from polar coordinates to rectangular coordinates. Let's go ahead and plot that point. 8 comma pi over 6. So I'm going to come out 8 circles. 1 circle, 2 circle, 3 circles, 6 circles, 9 circles. Oh, there's 8 circles. And then I'm going to follow the circle for r equals 8 up to the angle of pi over 6. And that gives me the point 8 comma pi over 6. Okay, now our task this time is to kind of do the opposite of what we did in the first example. In the first example, we started out with a point in rectangular coordinates, and we used some basic trigonometry to convert that to polar coordinates. We used the Pythagorean theorem, and we used the tangent. But now we're going to do the opposite. Okay, we know r is 8. We know theta is pi over 6. But can we find the x and y coordinates? X equals what? Y equals what? Okay. Well, let me start with x. Okay, and I want to use what I know. I know the hypotenuse, I know the angle, and I want to find the side that's adjacent to the angle. Well, the trig function that relates the adjacent side to the hypotenuse is cosine. So I'm going to say that cosine of theta, well, I don't know why I can't write a cosine right. Let's try that again. Cosine of theta would have to equal x over r. Now I'm trying to find r, so it makes sense to solve that for x. So I'll put the r up here with the cosine. I'll say that x equals r cosine theta. But r is 8. And cosine is pi over 6. Cosine of pi over 6 is square root of 3 over 2. So x equals 8 times the square root of 3 over 2. So that would be 4 square root 3. Oh, okay. This point's kind of similar to that other one. It's kind of backwards. And let me see then. Let's find the y value. We'll do something similar, but for our angle theta, y isn't the adjacent side, it's the opposite side. So if I want to relate the opposite side to the hypotenuse, I'm going to use sine. So I'm going to say, hey, sine theta would equal y over r. So again, if I put the r with the sine, I could say y equals r sine theta. So again, y would be 8 times the sine of pi over 6. The sine of pi over 6 is 1/2. And again, if you don't have this stuff committed to memory, no big deal, use your calculator. I think as you start using these again, some of these will start to just naturally, you'll naturally rememorize them. Alright, so my x coordinate is 4 square root of 3. My y coordinate is 4. Let's go over to Desmos and graph that. So let's get rid of this one. This is the one we graphed before. Now we're looking at the point 4 square root 3 comma 4. Now even though I've got the polar coordinates showing, Desmos always graphs points using rectangular coordinates. So if I flip back to my rectangular grid, I can see that I have a point that is over almost 7, about 6.9, and up 4. So these are rectangular coordinates we put in, and I can see that they're I can see that they're correct here. Okay, I can see that what I mean is I can see that they're rectangular here. But then if I flip my grid over to polar, I can see that the point I've really graphed could also be thought of as the point with an r value of 8 and an angle of pi over 6. Okay, so the polar form is 8 comma pi over 6, and that's just a confirmation that we converted it correctly. All right. So we saw that if we want to convert from rectangular over to polar, we have to use the Pythagorean theorem and the tangent function. And if we want to convert from polar to rectangular, we have to use cosine and sine. The book has a nice summary of that on page 643. So let's have a look at page 643 in the book. All right. Theorem 7.4, converting points between between coordinate systems. Okay. So these first formulas are the ones we just used. These formulas allow you to plug in r and theta and come out with x and y. So if you know r and theta, then r times cosine theta gives you x, and r times sine theta gives you y. The second formulas are what you use if you know x and y, and you want to get r and theta. Okay, the first one's really just the Pythagorean theorem. R squared equals x squared plus y squared. And of course you would have to take a square root to actually get r. And the second one is really just the definition of tangent. Tangent of theta equals opposite over adjacent, y over x. And of course you'll have to take a tan inverse before you actually have theta. Okay, these formulas, you want to make sure you have these committed to memory. We'll definitely be using them a lot in this class, and if you move on to Calc 3, they're going to come up all the time, because you're going to keep using polar coordinates if you move on to Calc 3. They will be a big part of the course. All right, let's do an example from the book. Problem 145 was on my outline, just an example using these formulas. Alright, so for problem 145 in the book, it says, for the following exercises, find rectangular coordinates for the given point in polar coordinates. And the point that's given is 1, 7 pi over 6. Alright, now, because I know the polar coordinates, okay, I know the values of r and theta, then the formulas that I want to use are the formulas x equals r cosine theta and y equals r sine theta. These formulas allow me to plug in polar coordinates and get out rectangular coordinates. So x equals 1 times cosine of 7 pi over 6. Now, again, you could put that into your calculator. And you know what, maybe I will just to again kind of model what that would look like. Make sure you're in radian mode. Alright, clear that off. 1 times cosine of 7 pi divided by 6. Okay, that's negative 0.866. Now, it would be nice if we could put that in a clean form. Okay, I recognize that decimal as the square root of 3 over 2. Okay, it might not be a bad idea for you to write square root of 3 over 2 and square root of 2 over 2 down. Okay, here, let me do this here. Square root of 3. Oops, that was x root. Let me try that again. Square root of 3 divided by 2, 0.866. Okay, and then also square root of 2 over 2 is 0.707. It might not be a bad idea for you to jot those down off to the side somewhere just to have them to refer to, especially if you've got to rely on your calculator, because then you can see decimals like that and see, oh, I need to convert that back. Okay, so x is negative square root of 3 over 2. And then y is 1 times the sine of 7 pi over 6. Now 7 pi over 6 is pi over 6 past pi. So it's going to have the same sine value as pi over 6, except that since it's in the third quadrant, it's going to be negative. So that one is going to come out to be negative 1/2. Okay, let's just check that real quick. 1 sine 7 pi divided by 6. Yeah, negative 0.5. Oh, so this is y, not x. Y equals negative 1/2. All right. Well, pretty straightforward. Let's go ahead and go back to the outline and see what else there is to do. Okay, we did problem 145. Now this is kind of the opposite. Previous problem we were starting out in polar coordinates and converting to rectangular coordinates. But here I have rectangular coordinates and I'm going to convert over to polar coordinates. So let's have a look at that. So in my example I'm given negative 5, 5, and I'll just make a little note to myself that these are x and y values. I was given rectangular and I'm supposed to come up with polar. So in this case, when you know x and y and you want to find r and theta, then you should use the formulas r squared equals x squared plus y squared and tan theta equals y over x. Okay. Well, okay, so r squared equals negative 5 squared plus negative 5 squared. So that would be 25 plus 25. R squared equals 50. Now when I take the square root of 50, well, 50 is 2 times 25, so I could break that down as 5 square root 2. And that would be a good way to put my r value. Although I will tell you, in most cases it's okay if you use decimals, if you don't preserve an exact form. Okay, it's not really going to bother me that much. Okay, and in fact, unless I specifically tell you to give me an exact form, I'm really kind of giving you a choice. So if the exact forms mess with you, just get decimals. Just get decimals, that's okay. Now, to complete this, I need to find the value of theta. So if tan theta equals y over x, then I can take tangent inverse. Well, let's first say that tan theta would be negative 5 over negative 5. So tan theta would be 1. Now if I take tan inverse of 1, well, I can ask my calculator what that is. Tan inverse of 1. Alright, there's my answer as an angle in radians. If I divide it by pi, I get 1/4. So that must have been pi over 4, or 1/4 pi. Okay. But you know what? Pi over 4 is actually not the answer we're looking for. If you think about it, this point goes left and down, so it's in quadrant 3. But that angle, that's 45 degrees. That's in quadrant 1. Okay, there's actually kind of a limitation with taking tan inverse. Okay, that limitation is that for any angle, the angle that is 180 degrees off from it has the same tangent. So in particular, if I go 180 degrees off of pi over 4, that'd be pi, so pi over 4 plus pi is 5 pi over 4. It's true that tangent of pi over 4 is 1, but also if I take that angle that's 180 degrees off of pi over 4, it also has a tangent of 1. Okay? There's always, even if we're confining ourselves to 0 to 2 pi, there's always two angles that correspond to any given tangent value. Okay? Which means that when we take tan inverse, we might not actually get the right one. Okay, we might get an angle that's 180 degrees from where we want to be. Tangent inverse will always either give you something in quadrant 1 or something that's in quadrant 4. But if the angle that you're looking for is in quadrant 2 or quadrant 3, then you're going to have to add pi to whatever tangent inverse gives you, okay, to get your right answer. So in this case, theta is not pi over 4. Theta is 5 pi over 4. That puts me in quadrant 3. Let's look at that in Desmos. So here was our point, -5, -5. Oops, -5. Okay, I can see it down there in quadrant 3. But the polar coordinates clearly are not pi over 4. That would be up here. They're 180 degrees off. 5 pi over 4. Now the r value we had was 5 square root 2. Let me see. 5 square root 2 is a 7. It's a little over 7. So am I 7 circles out? Well, let me see. This circle is 2. This one's 4. This one's 6. That one's 8. So yeah, I'm just a little over 7 circles out. My r value's right. Now, that's something you've got to be careful with polar coordinates. Sometimes when you take tan inverse, you have to add pi to the answer to get to the right quadrant. But the good news is, you should know what quadrant you're in if you had rectangular coordinates. So you should know right away whether or not your angle is the right angle, or if you need to add pi to it. Alright. Let's do problem 139. Okay, that's the next thing on my outline. There we go. There's problem 139. What do the directions say? Now I've got to come down here. It says, for the following exercises, the rectangular coordinates of the point are given. Find two sets of polar coordinates. Okay. And they want angles between 0 and 2 pi. Okay. Round to 3 decimal places if needed. Okay. Alright. So our point is -6, 8. That's in rectangular coordinates. So let me jot that down. And now I'll flip our view over. So I'll put an X and a Y just to remind myself that what they gave me was rectangular coordinates. So since I know X and Y and I want to get R and theta, then I'm again using these formulas from that theorem we looked at. R squared equals X squared plus Y squared. And tan theta equals Y over X. Alright, so R squared equals -6 squared plus 8 squared. So let me see, that's 36 plus 64. So R squared equals 100. Oh, R is 10. Boom. Okay, now tan theta equals 8 over -6. I could simplify, but it's not going to do a lot for me. This is not one of the nice angles that we would have the tangent memorized for. So I'm just going to have to go ahead and take tan inverse. So tan inverse of 8 over -6. Let's see what the calculator says. tan inverse 8 divided by negative 6 is negative 0.92. It said round to 3 decimal places, so I guess I'll do this. I'll say it's approximately negative 0.927. Now I'm going to show you something here that I think would be helpful for interpreting that. Okay, we could divide that by pi, I guess, like we've been doing. Divided by pi. So it's not a nice fraction. Okay, it's about a third of a pi, but a little less than a third of a pi in the negative direction. Here's something that would be useful, I think. Alright, so that's 0. This is pi over 2. Pi over 2, if I punch that up on my calculator, is about 1.57. This is pi, which of course is about 3.14. And then this angle down here, this would be 3 pi over 2. That's about 4.71. Okay, that's kind of helpful. It helps me figure out where this is. This is negative, so I know I'm going clockwise. But 0.9 is less than 1.57, so I know I'm not going to make it all the way to the y-axis. Okay, I'm going to make it maybe this far. So that angle is in quadrant 4. But check this out. Our point is left and up. Negative 6, positive 8. So my point shouldn't be in quadrant 4. It should be in quadrant 3. Left and up. So tan inverse gave me an angle in quadrant 4. I'm going to have to add pi to that in order to get the angle that I want. So theta equals not tan inverse of 8 over negative 6, but tan inverse of 8 over negative 6 plus pi. And it's the x and y coordinates that tell me I've got to add that plus pi. But I have to interpret where I'm at first. Alright, so there's that. But let's tack on a plus pi. 2.214. Okay, that's my theta value. So my polar coordinates pardon me. My polar coordinates are 10, 2.214. Now it said give it 2 ways. So here's what I could do. I could add another pi to it. That would swing it back down to quadrant 4. But as long as I put a negative on the 10, so if I add another pi to it, what's that do? Plus pi. Alright, now that's bigger than 4.71, so that swung me back down to quadrant 1, or quadrant 4. But if I put a negative on the 10, even though my angle's in quadrant 4, that'll keep me back up in quadrant 2. So that was 5.356. So there's my two forms of polar coordinates that use theta values between 0 and 2 pi, which is what the problem asked for. Alright, that's a good problem. Good little review of trigonometry. Yeah, sometimes when you take a trig inverse function, you've got to make an adjustment. Fortunately, it's easy to adjust for tan inverse. If you're not in the right quadrant, add pi. Okay, or add pi again and then reverse the sign of r. Alright, well, let's see what else is on our outline. Okay, definitions of polar axis and pole. Okay, these are just some terms that you're going to hear, so I thought they would be worth having a look at in our book, page 645. Alright, so here we are at the bottom of page 645 in the book. Okay, it says the line segment starting from the center of the graph going to the right, which we call the positive x-axis in the rectangular system, is the polar axis. Alright, so the positive x-axis is the polar axis. Okay, the center point, or the origin, is the pole. Okay, so in polar coordinates, we think of the origin as being kind of like a pole that we're swinging around as we plot points. Okay, and that's the source of the name polar coordinates. It's really similar to the idea of Earth's pole. So to think of this like this, you can imagine like you're looking down on the North Pole. The origin is the North Pole, and then these radial lines would actually be lines of longitude measuring angles horizontally around the globe. So that's kind of the analogy they're making. Alright, well, let's head back over to the outline. Alright, in rectangular coordinates, the curves that have the simplest equations are horizontal and vertical lines. So for example, I'm going to graph x equals 3 and y equals negative 2 in Desmos, but I bet you already know what they look like. Let's do that real quick. Maybe we'll flip our grid back over to rectangular. So if I type in x equals 3, it gives me a vertical line, and it's the vertical line where all the x values are 3. Okay, the idea is that this equation puts a restriction on x, but it puts no restriction on y. So it gives me all the points that have an x value of 3, no matter what their y value is. Okay, and that gives me a vertical line. Now if I type in y equals negative 2, it gives me a horizontal line made up of all the points whose y coordinate is negative 2. And again, there's no restriction in that equation on x, so x can be anything from negative infinity to infinity, but y has to be negative 2. So horizontal and vertical lines make for the simplest equations in rectangular coordinates. But how about polar coordinates? In polar coordinates, the curves that have the simplest equations are circles and lines. Now think about it like this. In rectangular coordinates, our grid is marked off with horizontal and vertical lines. Okay, that helps us track our points. For example, I could think of the point 3, negative 2 as just being the intersection of the vertical line x equals 3 and the horizontal line y equals negative 2. Okay, but if I flip over to the polar grid, now instead of having vertical and horizontal lines marking off positions, I have radial lines and circles. And I could think of a point like this point here as being the point that is on the circle for r equals 4, but on the radial line for pi over 4, or 45 degrees. Okay, so here it's radial lines and circles that are marking my coordinates. So radial lines and circles will actually be the easiest things to graph in polar coordinates. Okay, what did I say to graph here? I said do problems 154 and 155. Let's have a look at those. Those are they're examples of what I'm talking about. Alright, here's problems 154 and 155 in our book. The directions are on the previous page. They say for the following exercise, describe the graph of each polar equation, confirm each description by converting into a rectangular equation. Alright, well let's start with 154, r equals 3. Okay, if I go over to Desmos can actually graph that for me. R equals 3, and look what it graphed. It just graphed that the circle that has a radius of 3. Okay. Basically, in this equation, I nailed down r as being 3, so I want all the points that are 3 units away from the origin. But this equation puts no restrictions at all on theta. Theta can be anything. So it's kind of like where I got a horizontal line, only in this case what's varying is not x or y, it's theta with a fixed r value, and that swings me around and gives me a circle with a radius of 3. So I mean, really, a circle with a radius of 3 centered at the origin is a very simple thing to graph in polar coordinates. Its graph is just r equals 3. Okay. Now let's check that out on paper real quick. So I was given r equals 3. Now let me jot down some formulas I have here. I've got r squared equals x squared plus y squared. I've got tangent of theta equals y over x. I've got x equals r cosine theta, and y equals r sine theta. Now I told you need to memorize these formulas, okay, and we've been using them to convert individual points between polar form and rectangular form, but you can also use them to convert entire equations. This is the equation of a circle of radius 3 centered at the origin in polar form. But let's see if I can convert that to rectangular form. Okay, here's what I'll do. I'll square both sides of the equation. Okay, the reason for that is it allows me to now take advantage of this formula. R squared equals x squared plus y squared. So I'll let x squared plus y squared replace the r squared. And now I can see that, yeah, that is the equation of a circle that's centered at the origin. No shifts on x and y. And this side is supposed to be r squared, and that's what it is, the radius squared. So this is a circle centered at the origin with a radius of 3. Okay, I could enter that into Desmos and it would give me the same circle. X squared plus y squared equals 9. Okay, it just covered that purple circle over with a black circle. Okay, but it's the same circle. Alright, let's do problem 155. Okay, 155 was theta equals pi over 4. Now, unfortunately, Desmos can't really interpret equations that are stated as theta equals something. It can understand polar equations, but they have to be entered in solved for r. Okay, Desmos wouldn't know what to do with this, but we know what to do with it. This is a polar equation where theta is fixed at pi over 4, so even without drawing it, I could figure out what it looks like just by thinking about it. If theta is fixed at pi over 4, that means I'm fixed on this radial line. But then r can be anything since it's not even in the equation. It means I could be on any of the circles, but I have to be on this radial line. But of course, if r can be anything, r could also be negative, which means I could also be on the radial line that's 180 degrees off from r equals pi over 4. So what that gives me is it actually gives me an entire line running through the origin. And that's what any equation of the form theta equals something is. It's the equation of a line running through the origin. Now, I can use these formulas. Okay, I can use these formulas to convert that to rectangular form. What I need to do is I need to apply a tangent to both sides of this equation so that I can use this formula here. So if I apply tangent to both sides, then I get tangent theta equals tangent of pi over 4. Okay, now tangent of pi over 4 is 1, and according to this formula up here, tangent of theta is y over x. So I can replace the left side with y over x, and I get the rectangular equation y equals x, which of course is exactly what I'm looking for. Okay, if I type in y equals x, oops, I typed in y equals 4. Let's type in y equals x. This is exactly the line I was describing a moment ago. A line where theta is fixed at pi over 4, but r can be anything, including negative things. Okay, so these are the easiest things to graph in polar coordinates. Circles centered on the origin, and lines that go through the origin. But of course we can graph lots of other things with polar coordinates too. Otherwise we probably wouldn't be talking about them. So let's go back to our outline. Okay, in particular, we talked about how simple it is to give equations for horizontal and vertical lines in rectangular coordinates. Let's convert those over to polar coordinates, just as kind of a nice starting point for practicing the skill of converting between rectangular and polar coordinates. So we'll start with x equals 3. Now again, I want to try to make use of these formulas. Okay, here's a formula that has x, and now remember, my goal is to convert to polar form. So this one seems well suited because it allows me to replace x with polar stuff, r and theta. So since x equals r cosine theta, I can replace the left-hand side of this equation with r cosine theta. And now I've really done what I was supposed to do. Okay, but one more step. It's now in polar form, but usually with polar equations we solve them for r. Desmos won't really understand it any other way. If I don't have it solved for r, Desmos won't know how to interpret it. Okay, Desmos can understand equations of x and y that aren't solved for either variable, but for polar equations it seems to need to have them solved for r, and that is usually the convention. Okay, in most places there's an expectation that a polar equation be solved for r. Let's see what that looks like. Okay, so remember, this is really, let's get rid of all this other stuff. This is really the line x equals 3. That's rectangular form, but in polar form it's r equals 3 over cosine. Now if I want theta, I need to type it, theta. Now notice it just put a green vertical line over the blue vertical line because it's the same thing. Okay, which means we converted it correctly. Now what was the other one? The other one was y equals -2. That's in rectangular form. I want to convert it to polar form, which means I want r's and thetas. So if I look back at my list of conversion formulas, it looks like this one would be a good choice because I can straight up replace y with something that just has r's and thetas. So if y equals -2, then r sine theta equals -2. And again, if I solve for r, I get -2 over sine theta. Let's see if that gives us a horizontal line that goes through y equals 2. Alright, so r equals -2 over sine theta. Boom, it did it. Yeah, right there. Gave me a horizontal line, goes through y equals -2. Okay, if I flip back over to rectangular grid there, that just makes it even more obvious. Okay, well, what else do we have on our outline? problem 163, but I'm adding something to the instructions. Problem 163 gives us a polar curve and asks us to convert it to rectangular form. But I'm kind of adding into that first I want to sketch this by plotting some points. Then we'll convert it to rectangular form, and that'll kind of help us to know whether or not we did it correctly. Alright, let's have a look at this problem in the book. Alright, here's problem 163. It says, for the following exercises, convert the polar equation to rectangular form and sketch its graph. But as I mentioned a moment ago, we're going to sketch the graph first, just because I think it would be useful to do at least one polar graph where we plot points. Alright, here's the equation. R equals 4 sine theta. So we're going to look at this using some polar graph paper. Okay, I'm going to scoot that over just a bit there. Yeah, there we go. Now, we usually solve polar equations for R, so we think of theta as the input and R as the output, which I know is a little backwards. We're used to writing the input first and the output second. But with polar coordinates, R always comes first, theta comes second. That's just how we do it. Alright, so when theta is 0, R would be 4 times sine of 0. Well, sine of 0 is 0. So it means that the very first point is the point 0, 0. And the thing is, in polar coordinates, any point whose R value is 0 has to be the origin. Only the origin is 0 units away from the origin. Or I should be calling it the pole. Okay, should be calling it the pole. Alright, pi over 6, we plug that in. Sine of pi over 6, that's a half. 4 times a half is 2. Alright, so I want to go out to my second circle. You know what? Let's I want to go out to my second circle. Circle, circle. And I want to go to pi over 6, which is here. There we go. Alright, pi over 4. Sine of pi over 4 is the square root of 2 over 2. Times 4 would be 2 square root 2. 2 square root 2. Yeah, it might help if I use my calculator, just so I know about how far out I'm going. 2 square root 2 is 2.8. Alright, so on the pi over 3 radial line, I want to go out 2.8. 1 circle, 2 circle, 3 circles, so I'm about here. I'm just before that third circle. Okay. Oh, you know what? That's wrong radial line, not pi over 3, pi over 4. Alright, pi over 4 would be halfway in between the pi over 6 and pi over 3. So it'd be about like that. Alright, now for pi over 3, when I plug pi over 3 into sine, I get square root of 3 over 2, or times 4, 2 square root 3. Well, let me see. What's 2 square root 3? It's about about 3.5. Alright, so that means that on this radial line, I want to be at like 3.5. There's 3, there's 4, here's 3.5. Okay, in between the third and fourth circles. Now at pi over 2, sine of pi over 2 is 1, but when I multiply by 4, I get 4. So up here at pi over 2, I should be here on my fourth circle. Alright, well, let's keep going. Okay, that's not 2 pi, that should just be a pi there. Okay, my next radial line is 2 pi over 3. When I plug 2 pi over 3 into sine, it's going to be the same as when I plug pi over 3 in. Okay, so when I plug 2 pi over 3 in, I'm going to get 2 square root of 3 again. Which means I'm basically going to have this same point, but over here. And you know what? When I plug 3 pi over 4 into sine, it's actually the same as when I plug pi over 4 in. They both have a 45-degree reference angle. So this point is also going to be repeated over here. Okay, I'm going to get that 2 square root of 2 again. And you know what? I'm going to get a 2 again on this 5 pi over 6, this radial line here. And when I plug pi in, I'm going to get 0 again. So I'm back to the origin. I've completed the loop. And what I've drawn looks a lot like a circle. Okay, and in fact, we can show that it is a circle by converting this equation from polar form to rectangular form. So r equals 4 sine theta. Now let me write out my formulas again. I recommend that until you feel like you've got these formulas memorized, just write them out every time you start a problem. That'll help you get them committed to memory. X equals r cosine. X is cosine. R cosine theta. And y equals r sine theta. Okay. Well, a lot of times I have to do a little something to make it so that I can use one of the formulas. But usually my manipulations are either to get an r squared, or a tangent theta, or an r cosine theta, or an r sine theta. Okay? And in this case, there's something I can do that kind of gives me a twofer. If I multiply both sides of this equation by r, I get r squared equals 4r sine theta. And the reason that's a twofer is because I can replace r squared with x squared plus y squared, and I can replace r sine theta with y. Now our goal when we're converting from polar to rectangular is to make it so that we have all x's and y's and no r's and thetas. So we're going to get it all at once. R squared is replaced with x squared plus y squared, and then the r sine theta gets replaced with a y. Now looking at this side of the equation, I would say that's a circle, but this side kind of messes it up a little bit because I'm really just expecting like a 4. That would tell me a radius of 2. Okay, having a 4y doesn't really quite fit the form of a circle. But remember what our graph looked like. Our graph, which I just foolishly threw on the floor to get it out of my way. My graph was a circle that wasn't centered on the origin. It was shifted up vertically. Its center is up on the y-axis up here. Okay, that's kind of a clue as to what should be happening. Okay, if it's been shifted up, then really rather than a y squared, I should have y minus something squared. Okay, here's how I'm going to make that happen. I'm going to put this 4y over here so that I have x squared plus y squared minus 4y. I'm going to leave a little space. Okay, now there would be a 0 here, but I'm going to use a little algebraic trick called completing the square. Okay, to complete the square, I'm going to take the coefficient of the degree 1 term. So I'm looking at these. I'm going to try to turn this, the y squared and the y term, into a perfect square trinomial. So looking at those, I'm going to take the coefficient of the degree 1 term, that negative 4, I'm going to divide it by 2, and I'm going to square it. That gives me negative 2 squared, or 4. And then I'm going to add 4 to both sides. Now that's looking better on the right side because now I can see my radius squared taking shape. Okay. And on the left side, y squared minus 4y plus 4 is y minus 2 squared. And that looks right too, because if I've got y minus 2 squared, that tells me that I should have a circle with a radius of 4, I'm sorry, a radius of 2, and a center that's shifted up to y equals 2. Okay, but no horizontal shift on it. Okay, let's look at this thing in Desmos and see if that all looks right. Alright, let's get rid of all this stuff. Alright, so here was my original polar equation. R equals 4 sine theta theta. Well, you know what? That does look an awful lot like a circle whose center is shifted up to y equals 2 and has a radius of 2. Let's put in the rectangular form just to make sure we get the same thing. X squared plus y minus 2 squared equals 4. Well, yeah, I just drew a red circle right over the black one. It's the same thing. We did it correctly. Now, technically, for purposes of answering the question, we were really done. We were really done like right here. Because here, there were, instead of r's and thetas, there were x's and y's. So we had done what the problem asked us to do right there. Okay, we converted it to rectangular form. This would have been an acceptable answer. But going a few more steps just helped make it clearer that we had done everything correctly. Still have the same circle. Alright, I got one more thing on the outline I want to show you. This is something I think is kind of neat, and it helps kind of get to the essence of what these coordinates are about. So, let's flip to the outline. One last page on the outline, page 4. Alright, in rectangular equations of curves, the easiest attributes of the graph to manipulate are horizontal and vertical attributes, because that's how these curves are constructed, okay, with coordinates that are measuring horizontally and vertically. So it's easy to manipulate those curves in those directions, either to shift them horizontally and vertically, or to do stretches and compressions that are horizontal and vertical for rectangular curves. Okay, so to demonstrate that, we're going to construct a rectangular equation for an ellipse that is centered at the origin with a horizontal radius of 2 and a vertical radius of 3. Okay. Let's go over to Desmos to do that. So we'll get rid of this stuff. Now remember that for an ellipse, if we're working in rectangular coordinates, if it's centered at the origin, we're going to have an x squared and a y squared. Okay, no shifts on those yet. If I set them equal to 1, I get the unit circle. Okay, but then if I want to stretch the unit circle to have different horizontal and vertical radii, what I can do is I can come over to the x squared, and let's say I want a horizontal radius of 2. I could put 2 squared, or 4, in the denominator of the x squared term, and you can see that stretched my horizontal radius out to 2. Okay, and if I want a vertical radius of 3, I can come to that y squared term and put 3 squared, or 9, in the denominator there, and that stretches my vertical radius up to 3. Okay, now we've already been reviewing the fact that if I want to shift the center, then I have to put shifts on x and y. So let's put x and y in parentheses. Let's say I subtract h from x. Okay. Let's tell it we want that slider to go from, say, -5 to 5 in steps of 1. Alright, so if h is 0, then the ellipse looks like it did before. But if I let h be 1, that shifts me to the right. If I let it be 2, it shifts me to the right further. Okay, or if I let h be something negative, So this would really be like if h is negative 2, then it's like we've got x plus 2 up there. That shifts me to the left. Okay. Likewise, it's pretty easy to do vertical shifts. Let's say I subtract k from y. Same deal with k. Let's let k go from negative 5 to 5 in steps of 1. So let's put h back at 0 and k at 0. Alright, if I make k 1, that slides me up. If I make it 2, it slides me up more and more and more and more. Okay? Or if I make k negative, now I'm really adding values to y, that slides me down. My point is, in rectangular coordinates, it's really easy to manipulate the horizontal and vertical position of your curve. You know, if you want to shift the curve horizontally, just add or subtract something to x. If you want to shift something vertically, just add or subtract something to y. I mean, rectangular coordinates are kind of like an Etch-a-Sketch, if you've ever played with one of those. You know, an Etch-a-Sketch has two knobs on it, and those two knobs basically just allow you to move the horizontal and vertical positions of your little drawing tool. Well, rectangular coordinates allow us to basically play Etch-a-Sketch with our curves. It's also pretty easy to let's take these back to 0. It's also pretty easy to mess with the horizontal and vertical stretch. Like if I put an A here on my X, okay, same deal, let's let A go from negative 5 to 5 in steps of 1. Okay, the default would be A equals 1, but if I make it bigger, then that gives me horizontal compressing. And if I make A negative, that gives me, well, actually, let me think here. What would be good is if I went from 0 to 5 in steps of like 0.1. Yeah, there we go. Alright. So there's the default. A is 1. If I make A bigger, that gives me horizontal compressing. If I make A smaller, but I keep it above 0, that gives me horizontal stretching. And I can do something similar with the vertical stretch. If I put a multiplier right on the y, so again, let's let B go from 0 to 5 in steps of 0.1. So here, if I make my vertical stretcher, the multiplier on y, bigger, that actually does a vertical compression. But if I let that b be less than 1, that gives me a vertical stretch. Okay, so it's very easy to manipulate horizontal and vertical properties of a graph when you're working in rectangular coordinates. But in polar coordinates, the things that are easiest to manipulate are dilations and rotations, because that's what r and theta are measuring in essence. R is how far you are from the origin, that's your dilation. Theta is how far you've rotated from the polar axis, the positive x-axis. So let's do this. Let's convert that ellipse over to polar coordinates and then play with it in polar form. So I think we're going to need our paper for a minute there. So what was our ellipse? We had x squared over 2 squared, which was 4, plus y squared over 3 squared, which was 9. That gave us our ellipse with a horizontal radius of 2 and a vertical radius of 3. Now, if I want to use these formulas, I'll tell you what, if I didn't have the 4 and the 9, I would definitely use the x squared plus y squared equals r squared. But since they're there, they kind of mess it up. I can't make use of that one, but I could still make use of these. I can always replace x with r cosine theta and y with r sine theta. So let me see. R cosine theta replaces x, so it gets squared and put over 4. And r sine theta replaces y, so it gets squared and put over 9. Well, at this point, I have now translated from rectangular form to polar form. I had x and y variables. Now I have r and theta variables. But Desmos is not going to know what I'm talking about unless I solve for r. And as I mentioned, that's a pretty universal convention, at least in every context I've worked with polar coordinates. That's pretty much always understood that if you got a polar equation, you're going to solve it for r if you can. Alright, so if I distribute those powers, I get r squared cosine squared theta all over 4 plus r squared sine squared theta all over 9. Well, since I want to solve for r, I'm just going to factor that out. R squared times cosine squared theta over 4 plus sine squared theta over 9 equals 1. And then I guess I'll just divide to get the r squared by itself. So r squared equals 1 over all that stuff. Now be careful, when you take 1 over the sum of two fractions, you can't just flip the fractions over. That only works if there's just one fraction. If there's two, you really can't do that. If you wanted to do any flipping, you would have to get a common denominator and then you could flip. But I don't really need to do that. In fact, all I really need to do now is take a square root and I'll be solved for r. So maybe I'll just write one last step and then we'll take it back to Desmos. So r should be the square root of 1 over cosine squared theta over 4 plus sine squared theta over 9. So hopefully when I enter that business there into Desmos, what I will get, if I've done this all correctly, is an ellipse centered at the origin with a horizontal radius of 2 and a vertical radius of 3. Definitely easier to build the ellipse in rectangular form. It would have been especially easy if we had used parametric equations. But let's get it in there in polar form and then see what we can do with it. Alright, so I think we're done with all this stuff. Alright, r equals square root of 1 divided by cosine squared theta divided by 4 plus 1 divided by, oops, not 1, sine sine squared theta divided by 9. Haha! Look at that! It almost looks like we knew what we were doing. Excellent. So there's our ellipse, horizontal radius of 2, vertical radius of 3. Now let's start messing with this ellipse. Before, the first thing I did was I added and subtracted numbers directly off of r and x and y. Let's do that with r and theta. So let's say I want to subtract h from r. Okay. Well, let me see. If h is 0, then nothing's changed. Let's make this go in steps of 1. Let's go negative 5 to 5 in steps of 1. Yeah, I like that better. But if I make h bigger, ooh, look what that does. It dilates the curve. It keeps the proportions the same. Okay, keeps the proportions the same or pretty close to the same. um, Actually, don't stay exactly the same, but it's stretching it both horizontally and vertically. Okay, because it's making r bigger. It's pushing everything further from the origin. Okay, think about it. When h is 2, this says r minus 2 equals this stuff. But if I solve that for r, that would be putting a 2 over on this side, over on the right hand side, and it basically just makes all the r values increase by 2. Now if I go the other way and I use negative r values, now I'm really decreasing r, and that causes my graph to collapse in on itself. And eventually it's not even an ellipse anymore. Look at that. Turns it into a little, looks like an infinity loop on its side there. Or maybe just kind of a wonky 8. Okay, but my main point is, in polar form, it's really easy to dilate it. Now, let's manipulate theta. Let's add and subtract things directly from theta. So maybe we'll use k for that. Add a slider for k. Oh, look at that. Here, let's take let's take k and say we want it to be from -5 to 5 in steps of 1. All right. Now check this out. When I start adding and subtracting things from theta, it causes my image to rotate. You know what? Maybe what would be better would be instead of doing like -5 to 5, maybe we should do like -pi to pi and rotate in steps of like pi over 6. Yeah. Alright, so yeah, I can rotate it by pi over 6 or 2 pi over 6 or 3 pi over 6, which is really pi over 2. Okay, and if I rotate it by pi, it actually goes back to looking the way it did before. Or I could go the other way. -pi just takes it in the clockwise direction. -pi over 6. And rotate it clockwise. This is really hard to do in rectangular coordinates. It's not impossible, but you wind up having to do some really heavy lifting mentally, some really heavy thinking. If you've had a linear algebra course, there's actually probably an optional section in your linear algebra book that you probably didn't cover that talks about how to get rectangular equations to rotate like this. Okay, and it specifically deals with ellipses and other types of quadratic equations. But in polar form, it is super easy to rotate curves. Okay, you rotate them by just adding or subtracting directly on theta. This is one of the big advantages of polar forms. They deal with rotations so much more nicely. Alright, well, that is pretty much everything I wanted to go over on our introduction to polar equations. So here's the textbook homework to do for section 7.3. And at this point, I'm looking outside. It's about 4 o'clock on a Saturday. It's looking pretty sunny actually for the first time all week, so I think I'm going to go cut some grass. You know, when I was a kid and my mom made me cut the grass, I never really thought of it as a privilege. You know what? That's not really true. I kind of did. I really thought it was better than just about any other type of work. Even then, I kind of enjoyed the fact that you could go out and enjoy the sun and just kind of think about whatever you wanted to. And yet you still kind of felt like you were doing something. Yeah, I kind of like cutting the grass. I'm going to go do that. You all take care. If you need anything, let me know. Be glad to set up a Zoom meeting. Otherwise, stay safe, stay healthy, persevere. We won't be trapped at home forever, but hang on a little bit longer. We can get through this and put this behind us. Take care, everybody.